Hey, all y'all. Alrighty then, here we go. A little self-referential action there, huh, Ian? I know. It brings back memories of, walking around the house with a cassette and a pencil, just spinning it to rewind the stupid thing. The worst was 8-tracks, because repairing an 8-track was just horrific, because they had this little fold in them, because it was a continuous loop, right? Those are really hard to fix. All right, we're going to continue on with files today. Yeah, they're fine. Oh, what, an 8-track in? Those are horrible. So the midterm results are posted. The median and the mean were really close to each other. Standard deviation was only like 2 or 3 or something. So one question. It was 80, I believe 89 was the median / mean. 88 for one, 89 for the other. So you guys did fine on the midterm. I appreciate that. And I'm cracking the whip on the graders for PS3, because PS4 is right on their heels. What I'll probably do is I'll publish the grades for PS3 probably tomorrow, just to put some fire underneath the graders. So some of them you guys will see your grades, and then the rest of you who hasn't been graded, those will appear as the graders get to them. Oh, I forgot the hex joke, Ian. What was it? Do you remember it? Oh, hex, dead. And what's funny is, like, I wasn't even thinking about the dead, like Grateful Dead. It was just, we use dead beef so often as a marker in memory, DEA, BEEF, the hex values. That's a real common marker for uninitialized memory. And so it's like, oh, dead. I just put dead in there. And then later on, I was like, oh yeah, Grateful Dead. Oh, yeah, who knows? Too fun. There's usually at least one joke answer in every test that I do. It's like when I used to be editor-in-chief of a technical magazine called 73 for radio amateurs. I was a ham radio guy. 73 magazine was huge. It was international. Not quite 100,000 subscribers, but it's a big, 260-page magazine every month. And when I ran it for a couple of years, every issue had a picture of a dog somewhere. Sometimes it was on the cover. I wrote an editorial every month. Sometimes it was in there. Sometimes we had one for, articles, but there was always a dog in every single issue. Well, PS3 came out before 4 is due. So now we got wrong. 3s should already, 3's being graded right now, right? I expect them to finish upgrading like within a day on 3, and then you're working on 4 right now. What are we up to? Is 4 the RPN one? 3 should be done. 4 is due soon, and then 5 will be I'll release 5 next week. Yeah, Mary, if you haven't seen a piece at 3 grade, let me know. Like, send me email. We'll check in on it. 4 is due tomorrow. Oh, and I think that tomorrow is also the last day to drop the class. Is that true? View calendar. Calendars. There's so many dates. So many weird dates. Oh, yeah, Ian. Let's see, summer 2020, fall, fond memories, huh? Spring. This is spring. Actually, they don't have it in there. It must be on some other calendar somewhere. Or is this 2020? That's spring 21. One of the calendars has the last day to drop. It's an academic calendar, graduation dates, semester dates, maybe. Ooh, withdrawal. There we go. Like, none of you guys need this. Spring 21. I don't even know how to read these things. What does all that mean? Med students, fall 20. Somewhere it says Friday is the last day to drop. And what happens on Friday if you drop? Do you still get charged for it, but it appears like as a W on your transcript? I don't know all the rules. Semester dates, maybe? Spring 21. April. Ah, here we go. Last day to drop a standard course W. Oh, gotcha. I think you do get charged. Credit to audit. There's way too many rules, you know? We should just be able to just show up and just hang out in whatever class you like. And just after 4 years, we send you on your way. Congratulations. I know, it's only a month left, right? Like, why would you? Who knows? All right, here we go. I've probably got to teach something here. Yeah, so grading is hard for some reason in this course. Like we've had a lot of trouble getting grades current. And part of that's on me. I need to start the graders earlier. Like I need to start the graders on 4 now. There's only a couple of people who've turned it in, but we need to start grading them now. But now they're all caught up in 3. Just not enough staff, I guess. And 5's coming out next week. 5 will be short. You only have a week for that one. All right. 5, by the way, the plan for PS5 is we will be reading in strings from a file. The strings will have infix mathematical expressions like 5 plus 2. You convert them to postfix notation, 5, 2 plus, do the evaluation, and then write the result to the file. That'll be the fun part. And actually, the interesting part of that bit is doing the conversion. You'll have to use a stack to do the conversions. And by the way, that was the whole reason that I've been a little ambiguous about the operator nodes on Piazza and talking about them. Like in my head, I know that at some point you're going to need to keep track of operator nodes because in the conversion process, you essentially push all the nodes and then work with them as you're popping them out as you're doing the convert. So at some point you're going to have to push an operator node. That's why the fields are in there. And somebody asked me straight up in A1s, like, do I need to push an operator node, for PS4? My response was, I don't in my implementation. When I see an operator, I just do the pops off the stack and then push the result back on. So there's not really any reason to push the operator at any point. But like, the field's still there. Creating a node, honestly, when we're grading this thing, if you create a node for an operator or not, like I don't kind of care about that. I'm more interested in, did you implement the algorithm properly? Is the stack done correctly? It's the concepts I'm mostly interested in. That's why we don't even run the code. There's no auto grade or anything. There's no reason to run it because I'm just interested in seeing the shape of your code. Did you understand like how to move a pointer around? Did you understand what a push or a pop meant? And if for some reason like you had some little bug so the thing doesn't run, I'm not going to penalize you on that. If you had the concepts down, like that's all really I'm looking for. And of course, I'm going to ding you on little, nitty things too, just to annoy you. Like, oh, used a single character variable name again. 2 points. Just because that's the only way that instructors get fun. So we just like torturing you. All right. So we're going to continue on with files. So yeah, Jonas is like, we know. Nah, that's not true. If it were up to me, I wouldn't do any evaluations. Literally, we'd just hang out and talk for a while, and then eventually you would have learned enough and you could move on. So Tuesday, we talked about files from the C standpoint. So we're looking at how do we open files, how do we write to them, how do we read from them, and so on. So that was fopen, fclose, printf, fscanf, fgets, those functions. So those high-level C functions. Today I want to take a look at it kind of from the other side, and that's kind of the mode that we're in, I think, at this point in the course. Like we'll look at something in C and then flip over to the system side and see how it's implemented or how it's used. Same thing here. So we talked a little bit about files on Tuesday from the C side. Today I'm going to flip it over, take a quick look on the system side to see how files are stored and implemented on that side. So that's the other side of files. That is the I can't, somebody told me on Tuesday who's saying that, and I can't remember. Who was it that's saying both sides now? I've looked at files from both sides now. Wasn't Judy Garland. Anyway, that's where we're heading. What you're going to find out is that the system, the kernel side, really, we're using just tables and tables and tables to keep track of stuff. Tables tend to be indexed from sort of a high level into really detailed level as you go down. So the high level tables will just have a little bit of information, but a key to get into the next level of table. And that table has got more information. And if we need even more than that, there's an index into the next table down. So we can dig down, the kernel can dig down as far as it needs to pull information out about files and directories. And it's just, they're just kept in tables. There's just tons and tons of tables. The tables tend to be tables of structures, structs in C. So let's talk about files themselves. So for a file system, or a file sitting on the file system, there's a standard called POSIX, which you may have run into in other courses. POSIX is the Portable Operating System Interface, and it describes, did I spell metadata? It describes the requirements for a standard way to approach files, and most modern operating systems implement the POSIX standard. Certainly all of the Unix Cs do. It calls for things like this, and this is not all of them, but some interesting bits, I think, from the POSIX standard. Like, what kind of file is it? Is it a regular file like we would use out of C? I'm storing data of some sort. Is it actually a directory or a link to something? Is it a pipe or a socket? Those are ways to talk between processes or across a network. But they're all files. Everything is a file in Unix, and it's kind of the beauty of Unix that all of these things, like if I'm talking across a network, or if I've got two programs that are sharing information back and forth, all of those interactions, almost every interaction we have with data looks like I'm using a file. And files have like a standard interface into them. It makes it really simple. Like, there aren't any special cases. Oh, you got a printer on the machine? The printer is implemented as a file in the kernel. You can write to that printer just as if you would write to a file. So it really, it's not even an abstraction. It's just like a uniform approach to handling data of any kind. And because it's uniform, it just translates to all parts of the kernel. It makes it really, really clean. It's a great way to handle it. So we're going to talk about some of these that came out of the POSIX standard and where they're stored. Things like how long the file is, which mounted device holds it. There's going to be IDs for the user, like who created this thing, who owns it, what group are they in, if they're in a group of accounts on a system, what are the permissions around that. All of these things are specified by the POSIX standard. And as I said, Unix in general implements these things. Most machines implement POSIX, most operating systems. So let's talk first about devices. So I mentioned a device ID here, which mounted device holds a particular file. Devices on Unix are defined in a directory called dev. Make sure they're over here. This is on what do I have, MD10. This is on a server that implements a RAID array on my network, just one of my machines. Did someone say dev? Dev. Dev, you must get some really amazing swag that has dev all over it. That's so cool. That'd be really fun to have a name like that. No, there's nothing called Perry in the operating system, unfortunately. I'll bet. So these are the devices that are on the file. Well, it's the devices on the machine, essentially. They're all listed in the /dev directory. And there's a whole bunch of them. You can see it sort of overflows over here. There's so many of these. Some of these are actually disk drives. For example, all these S guys, SDA, SDB, SDC, and so on, SG, all of those are physical hard drives on the machine. Again, this particular box implements a RAID array, so it's got a lot of physical drives in it. Some of these are They're solid state drives, SSDs. Most of them are physical, mechanical hard drives. Some of these are network interfaces. RAM is for if I've got RAM disk of some sort that I've got like a piece of memory set aside to look like an actual hard drive. I can use it that way. The console is here, which is cool. These TTYs, all these TTYs are terminals. TTY stands for teletype, which is what we used to use to get into these machines. So when you open up a shell, for example, you're going to get assigned a TTY to that shell, and that's the interface that I send characters back and forth. That's how I type commands, get responses from commands. So this stuff here, I've got a TTY. I can probably see it. Can I see this one? I actually don't know how to get information about the TTY attached to this terminal. I don't think it's going to be in the environment. It might be. Let's grep for TTY. Yeah, I don't see it. I've got the term. That's the iTerm program. I don't see it off the top of my head. There clearly is a way to figure out which terminal you're sitting on in a given process. I just don't know where it is right now. So there's some special ones down here too. So I've got random over here. If I need random data, I can read from random. It looks like a device on the system. It's really just a random number generator, pseudo-random. If I need zeros, a bunch of zeros, there's one called zero. I can just go to dev zero and off I go. There should be a null in here. Where's null? Is it on the other side? Yeah, here's dev null. You probably have heard that as in a joke, dev null. Like, oh yeah, I just sent that to dev null. Dev null is a data sink. Essentially, if you need to get rid of something, you can just send it to dev null. In fact, I probably have dev shell. Let's pop open a shell here. And make me root. Sweet. I do this a lot in my cron tabs. It's like here. Here's actually this isn't not this one's running. So there's some job running every 16 minutes, actually every 4 hours, and it's doing a wget, which is a web command. So it's making an HTTP request to this place, kidbo.com/cron. Stuff comes back from that. I'm not really interested in the stuff coming back. It's just that cron.php is going to execute something on the web server side. And so all the stuff that comes back from it, I just send into dev null, which means it just disappears. I don't have to worry about like deleting it or storing it. It just goes down. It's like a drain. It goes down a big drain. So that's one way to use dev null. But tons of devices, right? Just device after device after device. Some USB devices down here, just tons of stuff. It's because everything shows up as a file to the kernel. And so all of the little features that the kernel has, all the inputs and outputs and all the things it can do with data, they all show up in the dev directory because they're all essentially files from the kernel's standpoint. Very, very handy. We're going to talk mainly in this discussion about hard drives, like actual physical hard drives, and those are going to be the SD guys, SDA, SDB, and so on. You can get some information about the mounted devices. So all of these guys, not all of them are mounted on the system. So these are available to the kernel to use. Not all of them are in use at any given time. Oh, I bet I could do a PS. Hang on. PS, Does tell me the teletype numbers? I'm still looking for the TTY numbers, sorry. I don't see them there either. I thought that was a way to see them. That's gonna bug me now. But yeah, so not all of these are in use. When I need to use one of them, I'm gonna mount it. And mounting just means I sort of physically make it available to the kernel. And there's a command, mount. The mount command is what I use to attach one of these to the system. All of these are block devices that we're going to be talking about. Block devices are just, it's just like a disk that I'm going to send bytes to back and forth, as opposed to something like a pipe or a socket or something. I'm just sending sort of raw data across. These are block devices that have blocks of data on them organized in units, hard drives essentially. So here's what LSBLK gives us, list block. It lists all the block devices that are attached to the system, and you see these are all the S devices. So these are the hard drives: SDA, SDB, SDC, SDD, SDE. Oh no, there's SDGs in there somewhere. Probably didn't make the cut here. So it tells us some information, like what size is it? Is it read-only? Where is it mounted is what we're interested in here. The mount point is in the directory structure of this machine. Where does this thing appear? All of these devices can be mounted anywhere you like. When you create something, when you mount something, you just specify where you want it to be mounted. For example, let's say I had, let's see if I've got one. Hang on. I usually carry a thumb drive around with me. That's my hubway key. You can imagine that's a thumb drive. That's my fortune say. This is one of those inception things. So I got this in a fortune cookie, and I was like, oh my God, that sounds really specific. like specifically for me. Like somebody must have slipped this into the cookie at somewhere. And I just carried it around with me to remind myself. So the fortune says, when the moment comes, take the last one. It's like, it's so deep. It's like, when is the moment? How will I know when the moment is, right? Anyway, I think about that a lot. So let's say this is a thumb drive, and I'm going to use it for data. Like I'm working on some project, got a bunch of data, and I'll take this, the thumb drive, and I'll mount it, like I'll insert it into the system, right? So when I do that, I'm going to get something from the kernel. Maybe I can see it this way. Where can I see these? I thought it was dmessage. If I do a less of that, where are these going to end up? They're in the log directories. Is it boot messages? No, it's not. Some of these things has been too long. Anyway, you'll, if you're monitoring such stuff, maybe it's in system, cd /log. Drake it, blah, blah, blah. Well, dmessage at old, I guess. Or here's some stuff out of dmessage. So dmessage is a log file that's written to as the system is booting up. So you can see things like here. This is dmessage, and it says, oh, I found a device. I'm going to call it SDD. And then once I see that device, so that would happen when I inserted the USB key into the machine, the kernel would notice it. It would set up a link to it. It would assign it a drive number like SDE or something, or G or H or whatever the next one is. It's just like available at that point. And then I would need to mount it. So to mount it, I would say mount /dev/SDG if it's G, and then some place to mount it. So I might mount it in /home/Perry or /home/data or something. This stuff on this drive then would appear at /home/data. And then if there were any directories on the USB drive, then I could go from there. So I can mount these devices anywhere that I want to on the file system at any point. What? You guys kill me. I have no idea what you're talking about. You still kill me. So anyway, like this is where these guys are mounted. Now you see a bunch of storages on here because, as I said, this particular box implements a RAID array. So there's a whole bunch of devices attached to the RAID array itself. But here's like /boot. So SDD1 is a partition of SDD, and partition Oh, nice, nice. But you know, I could be popping up to the next dream level too. You just never know what's going to happen. So this is the device itself. SDD would be the device. That's the entire drive. And then we can partition the drive into chunks, like logical chunks. Maybe I just need a little bit for my boot files or something, and I'll use the rest of the disk for data. Like I can split up that disk into partitions. You can see them if you, like on a Mac, it's disk utility, you can see them. It's like I only have one drive here, unfortunately. But like here's a drive, and if I had partitions, you would see, oh, there's a, there'd be different colors here. I guess other volumes might be it. So there's a volume up here, 20 gig or so, that's not being used. I don't know what that's being used for, recovery or something. But I can just split up those devices into chunks, into partitions, and then use each partition individually. And in fact, I could mount them individually if I wanted to. Here I do. So here's SDD. That's the entire disk. The first partition on it is SDD1, and I mounted that at /boot. Let's go see what /boot looks like. /boot. Yeah, so that's what's in the boot directory on this machine. That's SDD1. So there's a physical drive called SDD. It's got a partition, number 1. That's what's stored on that partition. And these are actually kernel images. So these VM Linux guys down here, those are compressed Linux kernel images. When the machine boots, it's going to read the most recent image. Actually, it's going to read the one I asked for in Grub, but it's going to read one of these images and load that into memory. That's how the machine boots up. But it knows to look at the /boot directory to find it. And the same with SDD2. SDD2 is a second partition on SDD. It's actually divided into some logical volumes with the logical volume manager, volume 0, 1, and 2, and those are in different places on the file system. So it's still one physical disk, but pieces of it have been mounted all over the place. Part of it's mounted on root, 50 gig or so. 7 gig is mounted as a swap partition. We'll talk about swapping next week when we hit virtual memory. The rest of it is on home, almost the entire drive, almost 900 gig, almost a terabyte is at /home for user directories. And then everything else is based off of this /storage stuff. But the point of that is I can move these devices around. If I didn't want this RAID array on /storage, I would just unmount it. There's an unmount command, and then mount it wherever I want it to be on like /home /storage. Just move it. You can move the entire thing. All right, so here's about those mount points. Actually, that's kind of what I just said, right? Yes, that was just SDD. I was just pre-shadowing, getting ahead of myself, I guess. So you specify these. Now, for standard stuff, like it's, I guess it depends on what you're doing. For me, it's fairly uncommon to manually mount things because typically what I'll do is I'll bring a machine up, like this guy. How long has this been up? This guy's been up 272 days. So I took this down, last spring, probably into last spring. I take this particular machine down once a year, vacuum it out, and then just boot it back up. So it really is only booted once a year. And it's on a rack somewhere, and I typically don't touch it. So I'm not like mounting and unmounting stuff all the time manually. Instead, I go over into the Etsy directory. There's a file here called fstab, file system table. And fstab has information about what I want mounted. Actually, there's a better picture of it in a slide coming up, this one. So this is fstab on the same system, I think. I just neatened it up for you a little bit. But you can see these are the things I want to mount at boot time. I certainly need to mount boot. I'm also going to mount home, which is where the user directories live. And I'm also going to mount storage. Storage is, that's actually the RAID array represented by this MD10 virtual device. And then this column over here just tells me what kind of file system they are. A bunch of ext4s in here. ext4 is an extent file system. There's a couple of versions of that. I've got a swap file system, which we'll use for swap files. Again, we'll talk about that next week. Here's an ext4 partition for the storage, and so on. And then these numbers over here, these are indications of when to scan the drive for errors. Should I scan it at boot time? Should I scan it periodically? So most of these are zeros, meaning no, don't scan. Like the temp file system, this thing, it's just that. It's a temporary file system. It's created at boot time. It goes away when you shut the machine off. You're not saving anything in there. There's no reason to check it for errors. And so there's a zero there for the check. For the home directory though, where's home? Here, I want to check it at boot time and then periodically. That too, as I recall, means periodically. And checking for errors, it just scans like the physical media, looking for issues with bytes written on the media, reports them back and tries to fix any if it sees them. But this is set up ahead of time. And then when the machine boots, it's going to read fstab. It reads all of this information and mounts all of these guys for me on the file system. If I wanted to do them manually, the manual mount commands look pretty similar. I would just say mount and then this information just on a command line. You can see what's mounted. I keep hitting that and don't mean to. You can see what's mounted with the mount command. So that's what's actually mounted right now. If you were curious, you can see the status of devices also with the df command. What does that stand for, df? Disk file display file systems, maybe df. I don't know what df stands for, but you can do like df-h, gives me human readable numbers. So this tells me, oh, for this particular machine, df says that's the file system, how big is it, how much has been used, how much is available, etc. So root doesn't really change. I use almost all of that because I just partition that to be the size that I need. But the other stuff, like here's storage, I've got, what is it, almost 2 terabytes of RAID array sitting out there. Almost a tera is used, so it's about half used, and so on. I think I can see the inodes too, can't I? Yeah, that gives me inode usage as well. Oh, interesting. Free. What's that one look like? Storage. Oh, that's pretty clean. I haven't looked at those for a while. I'm just making sure they're okay. So some of these, are like swap and proc and so on. Those file systems, these kinds, those are built into the kernel. We don't really worry about those. The other ones, though, like ext4, ext3 is an earlier version. They're just formats for data on a disk, and you would format the entire drive with this sort of format, like FAT32. FAT stands for file allocation table, 32 for 32 bits. FAT32 is what Windows uses to format its drives. And by formatting the drive, you're just setting it up in a certain way that the kernel understands. It's just a standard that it uses to read and write data to and from the disk. RiserFS is it's actually a really interesting journaling secure file system that everyone stopped using when Riser, the guy who invented it, killed his wife and went to prison. So I know he became a bad guy and we stopped using the RiserFS. I think that project got forked into something else, because it really was a good design. He just had this unfortunate habit of killing people. It happens, CS people are just weird. We're a weird group. Yeah, that's right. It's like, oh, didn't see that coming. Oh, it was a huge scandal. I remember when it was going down, like the CS world was out of their minds. Yeah, it just happens. It does. You just never know. If we want to get even deeper, like we can start looking at like the physical drive itself. Like here, I'm using the fdisk command, F for format. I'm not formatting, fortunately, here. I'm just getting information. I did an fdisk-L for list. Fdisk by itself is actually a pretty powerful command, and you should only use fdisk if you know what you're doing, because you can really, really screw stuff up really badly with fdisk. And I know because I have done it several times. It's like one of those things where you screw something up and you're like, holy shit, I'll never do that again. And then a year later, it's like, oh, I did it again, you know? Like usually you have to throw the drive away at that point when you've screwed it up that badly. But like there's a lot of information here, right? So this is SDB. It's a terabyte drive. That's exactly how many bytes it's got on it. And then all sorts of information about heads and tracks and cylinders and all of this, and how big is a sector. This IO thing is what's the maximum, the minimum size and the best size to use to move data back and forth. For this specific disk drive, this is a Western Digital Red drive. For this specific drive, it likes 4K reads and writes. So it's going to try to write 4K bytes at a time. It probably has a buffer that's 4K wide, which is why it likes that. So it's always going to try to use 4K blocks, you know, chunks of data back and forth. What's its identifier in the file system and so on. Here's that, this is the partition on that drive. So this is the entire disk. SDB1 is a partition. This tells us where does it start? Like which block on the disk does it start at? It starts at block number 1. And where does it end? It ends there. And I could calculate out like how many blocks is that, because I know how many blocks per track are there. So I guess that is my cylinder size. That's my block size. So I've got 512 byte blocks. I've got that many cylinders. I'd have to do all the math. You could figure out like how big that thing was in terms of bytes by doing the math here. Well, let's look at these terms and see what they mean. Here are the terms. So this is a representation of a physical hard drive. So hard drives, if you were to tear one open, I should bring one with me so we could tear open. I used to do that in 101. That was always a great lecture. It was like, you know, let's find out what's inside a PC. And I put up a bunch of slides and everyone would be, whatever. But then I'd pull a machine out and a hammer and a screwdriver and just start beating the crap out of it and just tearing stuff up. Like I'd yank a hard drive out and just chisel the top off of it and fling it out in the audience so people would see. If you look inside a hard drive, there's a series of stacked platters like pancakes or CD, like they kind of look like CDs on top of each other. Each of those platters is an aluminum disc that's coated with a magnetic material and then an oxide on top of that, an oxide layer for protection. That magnetic material can be magnetized, obviously. If it's magnetized, it's a 0 in a particular spot. If it's not magnetized, it's a 1 or the other way around. So I can use the magnetic properties, magnetized or not, to indicate 1s and 0s. And that's what this little head is over here on the upper right. It's showing this little read-write head coming across the disk and either energizing or not to magnetize a portion of the disk. And these portions are really, really, really tiny. Oops, that's not what I wanted. Do it this way. There we go, sweet. So I usually stack these things. So instead of just one platter, there's gonna be several, 2 or 4 or 8 or something, usually not more than that in sort of consumer grade disk drives. But each of those platters, those things that look like a CD, they're divided into tracks. So if you imagine just a concentric circle, and then inside that, you know, another circle, inside another circle, and so on, just like on this diagram, those are the tracks. We say that the tracks are kind of grouped into sectors like this. So in a particular track, I might have a bunch of data all organized into a sector. And then if I look at the tracks kind of on each of the platters going down, sort of in this direction, that defines a cylinder. So in this image, the yellow piece would be 1 cylinder. So I'd have that each track on each platter, and there are 2 heads. There's a head on the opposite side of the platter as well as on top. Each of them would have tracks. So I'd have 2 tracks per platter, like 2, 4, 6 tracks. All of those combined give me a cylinder. And depending on how the disk has been formatted, these blocks, well, the blocks typically, like here, this little block here, those are usually 512 bytes. Now, the interesting thing about, Bernard says, what does the magnetic property tell us again? It's just an indication of a 1 or a 0. So if I magnetize a spot on the disk, that's a 1. If it's not magnetized, it's a 0, or the other way around, because I said it the opposite way the first time. So I'm just using, it's like a light switch. If the light's on, it's a 1. If it's off, it's a 0. If it's magnetized, it's a 1. If it's not magnetized, it's a 0. This head, by the way, this read-write head, it flies across, well, the disk itself spins. So all these platters are spinning really fast. Actually, in this diagram, they're spinning this way. So they're spinning really, really fast. The two common standards are 5,400 RPM and 7,200 RPM. So the platters are spinning really fast. The way you use these things is if I want to write a byte of data, well, let's say I want to read a byte of data. That's more interesting. I want to read a byte of data off the disk. Well, first I have to figure out where it is, and we'll get to that part. But to read those bits, the platter is spinning. Let's say the byte is on this top platter here. So the disk itself is spinning. I've got to take this arm that's got the little read-write head on it, this guy, so that thing. I don't understand how I keep brushing this and it keeps like moving, but then I can't move it back. I don't know why that happens. So I've got to move the arm to the correct track. And then I've got to wait. So like, let's say that it's going to be right there, right here. Like that's where the data is that I want, but it's over here. It's actually written over here. So I move the head to the correct track, and then I've got to wait for the disk to spin. That disk is going to spin in this direction. At some point, that data is going to spin underneath the head. That's when I do the read. If the next chunk of data is somewhere else, and that's usually how it works, now I'm going to have to move the head again and then wait for the disk to spin the data under the head, and then I can read that data. And normally the way a file is laid out on one of these things is there's a directory sitting in usually track 0. It's either in track 0 or the inside track. Outside or inside track is where the directory is going to be. The directory is just a list of the files that are on the disk. It's really a list of their inodes, inode numbers, which we'll run into next. Each file has a number. So there's a little table, it's a directory on the disk that says, oh, you want foo.txt. Okay, so the first block of data, the first 512 bytes, are going to be sitting on cylinder 2, track 1, platters, this head number 2. It's going to tell you exactly where on the disk that first piece of the file is. You position the head, you wait for the data to spin under it. I read it. At the very end of that block of data, that 512 bytes, is a pointer to the next location on disk where the next 512 bytes lives. It's a linked list, essentially, a singly linked list. You start at the top, you read to the end of that node, that block of data, and it points you to the next block of data, and you wait again. Now, normally we're going to put stuff in, like we like to put them in sectors, because what I'll do is I'll move the head to the right spot, and then because I've stored things in sectors, I can just say, oh, read this, then move out one track and wait again, move out one track, wait again, move out. It's a fast way to store stuff. But often it's just scattered all over the disk. Is it related to B trees? Actually, Jonas, I think it might actually. Like, I don't know for sure, but I think those data structures might be B trees because those are really flat, right? B tree only has 1 or 2 layers. And so it'd be really easy and quick to find the data you're looking for in the directory. Nah. Jonas, did you take the database course? I think they talk about that there, don't they? Or they should. Oh, in 112, oh, no kidding. Oh, cool. So, a file's blocks are going to be across several platters. Now, normally what we're going to do, though, like if we've got a big file, for example, it's going to be broken into these 512 byte blocks. It's going to be all over the place. But we'll try to organize it on disk in such a way that, like, the first part is going to be up here on this platter, and then the next part is going to be on the platter below it. So while I'm reading this part up here, I can position the head down here to where the next part's going to be. And then when I'm done reading up here, just read it down here because it should be coming right under the head. And then the third part's going to be down here and so on. So we try to organize files on the platters logically so I can read them as fast as possible. And typically these are going to go into a buffer of some sort. because what I don't want to do is like read a byte from the disk and then immediately tell the kernel, hey, I read a byte, look at that. Oh, look, I read another byte, look at that. Now, instead, we're going to wait till we have the whole thing, or at least chunks of it, big chunks, put them in a buffer on the disk controller, hardware on the disk. And then when we get, well, we're done. Now we can notify the kernel, oh, by the way, here's that file you're looking for. So we're going to buffer that stuff. Excuse me. Actually, that's usually a price differentiator, is how big is the buffer on the disk itself. This also applies kind of to SSDs, solid state drives. Solid state drives are organized more like memory. There's no moving parts, so I don't have heads and so on moving back and forth. There's nothing spinning in an SSD. It mainly looks like a memory allocation or memory access. So I'm going to have allocation tables on the disk. And as I said, it's typically in the first location on the physical media. That file allocation table, the FAT, is going to be just a directory of inodes and then where the first chunk of each of those files lives on the disk. And by the way, when you delete something, when I delete a file, what normally happens is you just delete the entry in the file allocation table. And all the bits of that file are still there. It's just that the directory entry has been deleted. That's why we can use forensic tools to go in and recover stuff. The bad guys deleted a bunch of stuff. Well, it just deleted the entry in the directory. Essentially, all that data is still on the drive, so we can go in and just those bytes. Once you get to the first block, you can follow the pointers to all the rest of the blocks. It's really easy to recover that file. And so if you're really a bad guy and you want to cover your tracks, you'll use a disk shredder of some sort or a file shredder. What that does is it deletes the directory entry, but it also finds all the blocks on the file and overwrites them with ones and zeros several times just to make sure that they're really gone. Each drive also has a super block. Actually, there's more than one super block. The super block contains information about the disk itself. So for example, like here's a couple of pages of stuff. This is what's in the super block for STD1. So that's a partition on STD. I use the dump E2FS command to get this stuff. And the super block contains everything you need to know about the drive. Well, everything the kernel needs to know. So like there's a lot of information here, right? What's the file system state? Is it clean or dirty? What should I do if I see an error? What's the OS type? These are numbers around how many inodes do I have? How many blocks are on there? Are there any reserved? Like a lot of statistical information and also config information as well for that drive. Here's some more stuff. It just keeps going on and on. Here's the first bunch of blocks, the first 8K blocks. Where do they live? Where are their super blocks? Which ones are free? Which ones are not free? And so on. Which inodes are available on this particular drive? And again, the inode is just the number for the file. There's just lots and lots of information. This all ends up in a table in the kernel so that anytime the kernel needs to know, it just looks up this information in its table. And I think I haven't looked at that code for a while. As I recall, it's implemented as a caching system. So this stuff lives on the disk. When the kernel needs it, it goes and reads it, but then stores it locally in a cache so it doesn't have to go back to the disk. Disks tend to be really slow. Very, very slow. All right, so that's a super block. The super block itself usually is spread out. So I've got copies of it. Like essentially each group of blocks, maybe 8K blocks, has their own super block. I just duplicate that data all over the disk. FAT32, I think, as I recall, duplicates it in 3 places. Linux duplicates it in more than that. It's everything you need to know to use the disk. If you lose that information, because it's just stored on the disk, right? If that block gets corrupted, you can't use the disk anymore. And so there are duplicates of it. And one of the really common things that I do, actually, knock wood, I haven't had to do it lately, a head will crash or something, a disk drive will crash, and it'll corrupt a super block. Well, I've got to go find where was the other super block. I got to go find the next one. I can use fdisk to find those. Where's my fdisk drop? Do we use fdisk up here somewhere? I thought that was the one I said it was dangerous, right? Just tab. Does this tell me where the super blocks are? I think this fdisk would have told me where the super block was if I'd let it keep going. But it'll tell me where the primary super block is and then where the duplicates are as well. And so normally to fix a disk like that, you would go find the duplicate super blocks, remount the drive, and point it to the new super block that you're going to use, and then repair the damage to the original files. Because usually it's not just the super block that's overwritten, it's data around it as well. By the way, this picture, talking about losing files and data, this read-write head is flying over the disk really, really closely. So, I've seen images of, here's a disk head, and like if this is the disk head, like the little circles, the disk head, like they show a particle of smoke next to it, and it's like this big sitting next to it. So they're really, really, really close to the platter itself. When a disk crashes, what we really mean is that a head crashed, and it just means that the head stopped flying for some reason and landed on the disk badly. Usually a head crash means that you're going to scrape up the aluminum that's under the head, because this sucker's spinning at 7,000 RPM. You drop, it doesn't have a lot of mass, but you drop a piece of metal on top of it, it's going to scrape some stuff up. So head crashes are usually pretty ugly. There's usually stuff rattling around in the drive after that. All right, so those are our super blocks. I keep talking about inodes. Let's see what they are. So inodes, again, it's a struct, and it holds information that the kernel needs about a file. So to this point, we've been talking about drives, disk drives, directories on those drives, block devices, and so on. So we've gone down from device to an individual file. It's the inode that keeps track of everything about the file. So it's you can use a couple of different tools for that. debugfs will dump inode information for you. You can use the stat command to do it. Here's information about a single file. This is a file called config. Here it is. Owned by Git, so it's a Git config file apparently. So I use the debug command here to dump information on that particular file on this device. And here's what I got. Here's its inode number. Every file on a device has a number, and those numbers are unique to the device. What kind is it? What are the permissions and flags and so on? How many blocks are there? These things are creation time, last access time, last modification time. I can't remember what CR time is. This extent means that I've got another block of information in another inode that extends this file, and so I can go and get the other piece of it from that inode if I need to. But this is stuff, again, this is going to end up in a table in the kernel, and debugfs really is just reading that table and printing out what the kernel sees. So this is the kernel's data on that particular file, on that particular file device, MD10 in this case. So you can see all the structs. Like here's a great reference to them. Open link. Like this thing, these are all of the Linux data structures. This is pretty much the same for most Unix boxes. This is the Linux version. Like some of these we're not interested in here, but here's a file, for example. This is the struct that defines a file on the operating system. What's its mode? What's its position right now? What flags are set and so on? What's its inode number? Here's the inode struct. What's the device number? What mode is it in? Who's the user? Who's the group? What size is it? These are that access time, modification time, and so on that we just looked at. Like tons of stuff in here, right? What kind is it? It can be one of any of these. It can be a pipe, it could be a socket, it could be just a regular block device. We've got a bunch of ext stuff on this system, so there's going to be ext inodes. And notice that there's an ext inode info, right? Let's go see if we can find it. So another one, like 2. Oh, it doesn't give it that one. So there's another struct that contains information about an ext formatted file system. Yeah, most of this other stuff we're not interested in right now. But see all these tables though? I mean, this is all kernel stuff, all information about the running system. So that anytime the kernel needs information, it goes looks in its tables. Most of our interaction, fortunately, is going to be through the higher level stuff. Like we're not going to really need to dig down to the system level when we're working with files. We're really just going to use fopen, fclose, fprintf, and so on. Here's what they look like. So we're going to use file descriptors. We've actually run into file descriptors already. Remember file descriptors when on Tuesday, we opened a file and the return value from fopen was a file pointer, capital F-I-L-E. That file pointer really is just a file descriptor. The descriptor is just an integer. So it's just a number that identifies an open file on the system. And they're used this way. So over here, I've got file descriptors for each process. Each program that's running gets its own table for file descriptors. And out of the box, when a process starts up, you get descriptors 0, 1, and 2 built in. 0 is standard in, 1 is standard out, 2 is standard error. So those are all probably attached to a terminal somewhere. And then here's some other file descriptors. I clearly opened up another file or two in here. File descriptor 4 for this process, for example, ends up being this home/joe/wikidb. These are per process, these guys, and then all of the processes running on the operating system, I combine all of those into a larger table, the file table, this guy. That's kept by the kernel. I mean, the kernel keeps all of these, but one is for an individual process. Another one, the file table, is everybody's file descriptors. So whenever I need to access a file in the operating system, I can look in here. If I've got the file descriptor, look in there, and then through there I can get to the inodes. And the inode uniquely identifies that particular file on the file system. It's going to give me an index into the first block of that data. Let's talk about permissions, because that shows up quite a bit in our discussion of files. So in permissions in Unix, we divide them into 3 groups of 3. So the 3 groups are the owner of the file, the group that the owner is in, and then everyone else. So those are the 3 kind of cuts at security for files, permissions essentially. So owner, group, everybody else. And then within each of those, I've got 3 values: read, write, or execute. Those are the 3 things I can do for a file. So I end up with stuff like this. So here's a file called lorem.txt. It's owned by Perry D in group users, and here's the permissions string. So again, these are groups of 3. So I've got RW space. That means that the owner of this file has read and write permissions, but not execute permissions. I don't need execute on a text file because I'm not going to execute it. The group that I belong to, so the users, everyone else who's in the users group, can read the file, but can't do anything else with it. They can't write or execute this file. And the same with everyone else. So I really have given myself read-write permissions. Everyone else has read permissions. But notice that like these are 3, right? So I've got 3 things here. These are really just flags. The read flag is either on or off. So it's a binary value. Same with write, same with execute. So I've got essentially 3 bits, 3 flags. What's 2 to the third? 2 to the third is 8. So in 3 bits, I can have 8 different values: 000, 001, up to 111. There's 8 of them. Well, if I'm working with groups of 8, it makes sense to write those values in octal, because octal, I can go from binary to octal like immediately, just 3 bits, and then I've got an octal number, right? So if I have a 7 in octal, it's 111. That's the binary for 7. It's really easy to bounce back and forth between the 2. And so I do things like this. So if I wanted, for example, read, write, execute for somebody, that's a 7. because a 7 in octal is 111 in binary. Each of those flags is set. So read, write, execute, all set. Here's just read, execute, 101. I leave out the write, so it's got a 0. And 101 is 5 in octal. Same in, here's just read permission. I set the read bit, so now I've got 400, 4 plus 0 plus 0 is 4, so that's a 4 in octal. And then I would just use the change mod command. And I know it's really change mode, but we get lazy, I just pronounce it change mod. Please do not, when you go on interviews, do not pronounce that chmod. Let's not pronounce chmod. It's either change mode or change mod. I would go with change mode on an interview just to make it clear that I'm changing the mode of the file. And then when you get on the job, you can switch to change mod. But never, please, ever say chmod. Or if you do, don't tell them you took my class, because I don't want to know. I don't want them to know that. Anyway, so I'm going to use change mod to change permissions on stuff. Like here, I'm just changing. This was, I used ls-l, list-long to give me permission information. So I've got read, write, execute. That's a 7. I've got 744 right now on this. And I want to change it so that everyone also has execute permission. So read and execute. That'd be 5, right? So that'd be the read, no write. That's a 4, nothing, and a 1 would be a 5. Read execute's 5. So I just change mode 755 on lorem.txt, and now I've got, there's the 7, there's the first 5, there's the second 5, and so on. That group information, by the way, you can get that from the passwords file. So if I go into Etsy, undo last password. So here's the passwords file for this particular machine. Am I at the bottom? Almost. Actually, not close. There's quite a few in there, huh? The passwords file gives us data about users on the system, accounts on the system. So for example, here's my account down here. Here's Perry. And you can see that this is the user number, 510. So I'm user 510. I'm in group 100. And if you look up, there's probably quite a few in group 100. Here's Colleen, that's my wife. She's user 507. She's also in group 100. So group 100 is the users group. And then within the users group, each individual account gets its own number. So 507 is the account number, the user ID, the group ID, GID is 100 in this case. And you'll see, these vary, right? So some of these are similar, some are not. Very often we'll see stuff like this. So user ID is 91, group is 91, user ID is 67, group is 67. That just means that these accounts are in their own groups. So they don't really interact with other accounts, just themselves. There's no sense to put them in other groups. And by the way, you can have more than one group. So my Perry D account, for example, that's just the Perry account. There should be a Perry D account in there as well. Grep for it. Password grep Perry D. So there's Perry D, user 501 in that case. I'm also a member of several other groups. So I'm a member of the Wheel group. Wheel is all the administrators. I'm in the admin group, the root group, and so on, because I'm an administrator on the box. There's an extra bit out here, that little dash right there. So that's read, write, execute, read blank execute, read blank execute. There's this little dash here. That's for a flag to indicate, among other things, whether this is a directory or not. So here's a directory. I make dir. Make dir says make the directory called lorems, and then list it. Here's the listing for it. And you can see there's a D now in that first bit. The D flag means that is a directory. That's the directory flag. If there's a link somewhere, like here I'm linking lorem.txt one directory up. I want to link it into this directory, and you'll see there's an L here. The L means that is a link. That's a soft link in this case. We'll talk about soft links at some point. But all that information is kept in the inode for each file. So when I change permissions, when I change set something up as a directory or as a symbolic link, that data is written into the inode for this particular file. That's how the kernel knows what this file is and what it's capable of. Cool, no? I don't get any sense, like, do you guys get any experience at all in like this level of like command line stuff, like system stuff? Do you see this in any other course? I don't think so. Maybe indirectly. I don't think so either. From a dev standpoint, like when you guys go out into the world, and like a lot of you are going to be software engineers, developers, like you're going to spend a lot of time on the command line, like a lot of time on the command line. Like, yeah, it's just my classes, right? Because I'm so like focused on that. So you must learn the command line. I just want you to be okay on the job, There's just stuff you need to know for work. And it's just nicer if you know it when you go in and not, having to teach you on the job. Oh yeah, well, of course Rich does it too. Actually, West and I are talking next week about 210 and 350 and how they interface with each other. And then just in general, what a systems curriculum should look like. Like what should you guys be learning to prepare you to go out into the job market? And surely this is going to be one of the things. All right, I mean, that's kind of a romp through file systems. Like the nice advantage to us is that, there's all these low-level functions. Like this is what the kernel's using. Like here, when I open a file using fopen in C, that fopen call is in turn going to call a lower level function called open. That's the one that the kernel's going to use. It's really similar, right? Like I'm going to open this thing called foo.txt, but then I'm going to pass in stuff like these are all my flags. I've got to create it if it's not there. It's going to be read write. If it is there, truncate it. Here's the initial permissions I want on it, and so on. Like all of that information is what the kernel's going to write into the inode when it creates the file for us. We're going to get a file descriptor back, and then that's going to be passed back to fopen. We'll store it in our file pointer. But this is going to do all the writing to those tables so that the kernel now knows how to get to that file and what's in it. And again, we have the advantage of the abstraction in the F series, like sounds like an ad, like fopen, fclose, all those. They abstract out a lot of these details for us, so we don't have to worry so much about them. You can, by the way, use open. That's it's in standard lib, I think. You can use open, close, and so on to do direct I/O to those files if you need to. It's just more convenient to use the abstract ones, fnode, fopen, fclose, and so on, I think. All right, so bottom line, like everything's a file. Everything's a file in Unix. It just makes things so clean. We don't have to worry about formats or anything. It's just a file, and we're just writing data or reading data to and from it. The devices themselves are high-level items. They can represent a physical device, a stream, a socket, something like that. Like anything we're going to move bytes across, we can identify as a device in /dev. And all of this stuff is stored in tables that the kernel uses to keep track of things. Our interface is a little more abstract, which is, I think, really, really handy. But you're just going to drop into the command line so often to tweak something, to fix something, to mount something. It's just so much easier to do on the command line. The system was built, like these Unix kernels were built, they were built without any sort of windowing. Like all their operating systems are command line operating systems. And then we added the GUI on top of it later on. So they were built to run from the command line. That's why there are so many tools and why they work so well with each other. So like just play around with the command line if you can. Like you're not going to break anything, I don't think. Or if you break it, just fix it, or just reinstall. Like it's not a big deal, I don't think. So play for sure. And somebody asked in A1 where this stuff is in the books. Most of this is from chapter 10 of CSAPP. Almost the entire chapter. All right, my droogs, that is it for today. 3:15, time to go home. Enjoy the weekend, should be nice. And I'll see you guys Tuesday. I won't release any problem sets before next week, and I'll get my graders whipped up to make sure they're great and stuff. Have a nice, thanks, Ian. Gabriel, I'll see you guys next week. Enjoy. Been fun, as we say. End meeting.